Hello dear students, let us start our discussion about circular current loop as a magnetic dipole. As we already know about the electric dipole, suppose that we have an electric dipole of charge minus q and plus q, and the midpoint of this dipole is O, this one is A and this one is B. Then if you want to calculate the electric field intensity at an axial point from the dipole which is placed at a distance of r, which is very large in comparison to the separation of the dipole, that is twice of L. So this one is L and this one is L. So what will be the value of this electric field intensity? This can be provided as 1 by 4 pi epsilon naught twice of P by R cube. We recall it at here because we want to discuss the circular current loop as a magnetic dipole. So we recall the electric dipole and what will be the amount of the electric field due to an electric dipole at any fixed point. Okay, so suppose that we have a circular current loop. This is a circular current loop and the radius of this circular current loop is taken as r. The current flowing through this circular loop is taken as I. So if we take a point on the axis of this circular current loop which is placed at very far distance, okay, so suppose that the distance of this point from the center of the circular loop is x. So what will be the value of the magnetic field at this point due to the current flowing through this circular loop? This will be provided by the formula. This will obtained with the help of the Biot-Savart law, and we will easily obtain the derivation for the magnitude of the magnetic field at this point and obtain that what? Mu 0 I r square divided by twice of x square plus r square whole power 3 by 2. And the direction of this magnetic field at this point is always along the axis. If the current is flowing in anti-clockwise direction, then along positive x direction. If the current is flowing in clockwise direction, then the direction of this magnetic field is minus negative x direction. Okay, so this is the magnitude of the magnetic field at this point. But if we choose this point such that this is very far away from the circular loop, it means the value of x is very large in comparison to the radius of the loop. It means x is taken as much large in comparison to the radius of the loop. So what will be the value of x square? This will be much and much larger than that of r square. So if we add or subtract this r square in the x square, then the term r square does not affect the value of this x square. So this can be taken as negligible in comparison to x square. So this b becomes mu 0 I r square divided by twice of, this can be taken as negligible, so x square whole power 3 by 2, 2 and 2 will be cancel each other here, this becomes x cube. Now we are seeing that there is a term of r square. So if we multiply by pi in this, then we get pi r square, that is the area of the loop. So if we multiply and divide by pi in numerator and denominator, then we get what? Mu 0 I pi r square divided by twice of pi x cube. Alright, so we can replace this pi r square by a term a, that is the area of the circular current loop. So from here we get what? B is equal to mu 0 I dot a divided by twice of x, twice of pi x cube. Now this I into a can be defined as a new term that is known as magnetic dipole moment. Magnetic dipole moment. Suppose that we have a circular current loop and there is a current flowing through the circular loop is I, and the area area covered by this circular current loop is A, then the product of this area to the current can be defined as a new term that is known as magnetic dipole moment. Magnetic dipole moment. Okay, so if we replace this Ia by term m, and also this m is a vector quantity. If the direction of current flowing through the circular loop is in anti-clockwise direction, then the direction of this magnetic dipole moment is always emerging out from the plane of this board. And if the direction of the current flowing through this loop is found in clockwise direction, then the direction of the magnetic dipole moment is always perpendicularly entering into the plane of this board. Okay, and it always perpendicular to the plane of this area. So if we replace this Ia by term m, then we get mu 0 m divided by 2 pi dot x cube. So from here we get what? B is equal to mu 0. As we know that the proportionality constant in Biot-Savart law is mu 0 upon 4 pi. So if we make this 2 pi as a 4 pi, then we get mu 0 by 4 pi. Then we have to multiply and divide by 2. That becomes 2m by x cube. If we compare these two formula, this and this, then we get mu 0 is replaced by 1 upon epsilon naught, and this m is replaced by that of p, and this x is replaced by r. Okay, so we are seeing that these two formula are analogous to each other. They are similar, and they provides electric field in the case of electric dipole moment, electric dipole, and magnetic field in case of magnetic dipole. So this is an electric dipole and it provides the electric field at this point, and in similar manner this is the magnetic field. So this magnitude of this magnetic field is obtained with the help of the magnetic dipole. In similar manner, so we can say that this circular loop behaves just like a magnetic dipole. Okay, and the magnetic dipole moment of this circular loop can be represented by a symbol small m, whose value is I into A. Okay, so in a similar manner we can write it as what? If you see at here that you have a circular loop of radius r, and there is a point P, then the magnitude of the magnetic field at this point P, which is very far away from the center of this circular loop, is mu 0 by 4 pi twice of m by x cube. Similarly, if we take the circular loop at here and we choose a point which is lying on the plane of this circular loop. So what is the plane of this circular loop? This can be formed like this also. So if we if we choose a point at here which is also very large in comparison to the radius of this circular loop, and this point is lying on the plane of this circular loop, so what will be the value of the magnetic field at this point? This will be equal to as the electric field intensity due to electric dipole at equatorial plane point. So this will be equal to mu 0 by 4 pi dot m by x cube, because if you choose an electric dipole, suppose that if you choose an electric dipole like this, minus q and plus q, so if we take a point at here, then what will be the value of the electric field at this point? You will obtain that the magnitude of the electric field at this point is 1 upon 4 pi epsilon naught P by x, r, if the length of this is r, then r cube. Similarly, this amount of the magnetic field will obtain due to this circular current loop at any point which is lying on the plane of the circular loop and is placed at very far distance in comparison to the radius of the circular loop. So these two important formula will obtained, and this provides us some knowledge about circular current loop always behaves like a magnetic dipole, whose dipole moment M can be defined as the current flowing through the area multiplied by the area of the loop. Okay, so this is all about the circular current loop behaves like a magnetic dipole. In our next lecture, we will discuss as a magnetic dipole moment possessed by an electron which revolves around the nucleus. Okay, till now, take care. Thank you.